Hi, welcome to the next episode of the weekly Raku reviews, and today we're going to review the second task of week number 77, which is called Lonely X. So let's look at the task. The task is here, so you've got a matrix and you have to find all those x's which are surrounded only by zeros, like here. Well, actually it's not a zero, it's a capital O. You're given a matrix m by n, and it contains x and O's. Write a script to count the total number of x's surrounded by zeros only. Print 0 if none found. Right, so this x is the lonely one. These two are not, because their neighbors are, well, zeros and x's. So you see, and here, like this one, and that one, these two are okay, and these three are not. Right, so let's look at the solutions actually. So we see once again, so write the script to count the total number. So basically the official task is just to print the number of such items. Right, let's go to the list of solutions in the Raku programming language. And here it is. So the first solution in the alphabet is Arne Sommer, and here is the solution. So what we have here is basically the main subroutine. The whole file covers the main subroutine as unit sub. So it takes the matrix from the file, so that's the file name obviously. So there's this matrix 1, I believe there's a file we can see here, right, and there's another one, probably it's the second example, right. So we are reading it, so we're reading all lines, so this is how easily you can read a file, a matrix actually, into a variable. But after that you want to make sure that the matrix is, well, perfectly rectangular. So all the elements, so we get the lengths of all the rows, and the reduction operator makes sure that they are all equal. Right, the second thing is a single character in the right. So you take all the things and you count the number of characters in the items. And if there's something somewhere, something bigger than one character, then you will catch that. Okay, rows, columns. Okay, is lonely. That's the Boolean variable. Probably you can use actually false. No, sorry. So is lonely. I believe this is not the Boolean, right? So it's the is prefix tells me that it should be Boolean, but actually it's not. It's just a counter. So that's the number of lonely items found, which is the thing you have to print in the end, according to the task definition. Right, so then what you do, you just scan the rows, you scan the columns, and you increment this lonely if the element at this position in the given matrix. So this is the matrix. Basically, this is the array, and these are the current positions. If this is a lonely thing, and here's the function that detects this. So you return false if the current element is 0, well, is O. Then you scan all the neighbors, so you go left, right, up, down, and you either change both coordinates or you change only one. So that's why you have 3, like left, nowhere, stay at the position, go right, and the same here, go up, go stay in the position, and go down. Well, probably actually this is up, down, and this is it's like columns. This is left, right, but there's no big deal. And you have to skip the current position because you're not going to test the element with itself. Then you test if the element at that position. So basically, if that neighbor that you're trying to find here using these steps, if it exists, so you see, so the coordinates, like the current plus this shift and the column plus this shift, if this exists, so basically, because the matrix is not, well, and it has it has certain dimensions, so you can have an element x which you test currently, which is located on the edge or in the corner, and you have less than 8 neighbors, so you have to skip those which do not exist. This is what happens here. And then you return false if the neighbor is x. So as soon as you find the first x element in the neighboring position, you immediately can guess that this is not a lonely element, full stop. Otherwise, if you couldn't find something, so basically if you didn't have any chance to return from these loops, you return true, so it means that you found no x's around your current x. Yeah, and this is lonely item, and you can just increment the thing. Okay, so I believe we can immediately run this. Raku Arne Raku Ch 1. And what was that? It was Arne Raku matrix 1, right? Not that easy. Not that easy. What do you need to do? What is n? It's number 2, right? So that's why it didn't want to. Right, so there's only one element, and in the second matrix there are 2 elements. You remember that, like in the up right corner there were 2 elements. Okay, seems to be working. And the only thing I'd like to also see, well, basically which elements were found, but the task actually, yeah, formally doesn't require. Right, the second solution by Feng Chang. I really like that there are new names, well, at least for me, still, since I started these reviews. So, right, so we are reading the lines from the input, the standard std in. We're reading the lines, we push something to this a variable, and what we are pushing there is unshift o, push o. So we split in the characters, we convert it into array, we unshift the 0. So what is not unshifted? Basically you... okay, so yeah, unshift adds the item as the first element in this array, and push basically adds it as the same item at the end of the array. So you surround it with 2 additional, well, let me call it 0, 2 additional zeros, so that basically you increase the neighbor space, right? So for every element that you want to test, you will have a neighbor. This is what happens here. So, but we added the neighbor on the left and on the right side. But then I believe we will add more neighbors on the top and bottom levels, right? So there's so we added 2 stories to this building, and basically we have the matrix surrounded by zeros. Everywhere is 0, so we can safely check all the 9 numbers for every element within actually that circle, that fence of zeros. And right, so and then we have 2 loops. We scan everything, and we scan everything starting, you see, starting from 1 up to rows, and the rows is actually the number of the original elements, right? The number of rows in the original data set, and the width is the same. So yeah, it's these -2 is just to compensate these 2. And after that, there's a really clever thing. So there's the so-called all junction, and you want, so this is the junction, you save it in a variable. You will want to make sure that all of these are true. Well, actually not true, but actually all of these equal x. So it's not like you test that this is true like here in place, but you just create a junction of these 8 elements, and you see there are 8 neighbors. And after that you make this you check, you basically use this as a single variable. Imagine if there's like a single element like this one, a single neighbor here, and you compare its value with an O, capital O. But with the junction, you can actually you can compare all those 8 elements in a single go. So here you compare all elements. Basically, yeah, you can take this all and put it kind of somewhere here around, right? Around those, like all of these equal 0. This equals 0, that equals 0, this equals 0, and so on, so on, so on. And after that, you have this all. But you can also do it simpler, like this one. So this one is a junction, and it contains all the elements here inside, and all of them will be tested against this condition, which is really an amazing thing in Raku, how easily you can do that. But okay, so what am I going to do? So we're going to compare the neighbors, and also notice that you don't have to have 2 pairs of square brackets. You can use a semicolon. Why not? That's the way to separate the second dimension. And so yeah, so increment the counter if the current element is x and all its neighbors, so basically this missing element is x, and all other neighbors are zeros. Yeah, and we know for sure that we don't have to test if the element is on the edge, because we know that there are neighbors for each valid item. Right, so go Raku, Feng Chang, Raku, Chat 2. And yeah, the thing is that I want, maybe I can do it like this, right? So the answer should be 0. Actually, yeah, I believe we have to prepare the matrix. Okay, let me do it like OOX, OOO, XOO. So the answer should be 2, right? This element and that element, right? Let's try to enter this. Right, the answer is 2. Maybe run it again. XXX, X, O's, OXO. Now the answer should be 1, right? If I'm correct. And it is 1, right? So it is a good example of good programming. Right, so the next is Jason Messer, Raku number 2. So here's the thing. So there are 2 matrices, and we are going to test them both. So find no neighbors. So coordinates we are gathering. So I believe we are going to print the coordinates of so basically like first row, third item. So it's basically first row is 0, third item is 2, so it's 0, 2 should be printed here for this example. Right, so we're going to gather the coordinates, and we're taking them, I believe, only here, right? So we scan the rows, and this is x. Yeah, well, actually, yeah, I think this is y, right? And this is x. And then we scan the elements within the row. Then we skip if this element, skip the rest of the body if this element is x. So we only want why? We only want the elements which are 0. Next, next unless. Yeah, so we only want to test the element if there's this x inside this. Then that's another smart way of visiting all the neighbors. So how do we do that? We have 2 lists. We cross them. Basically, we make cross multiplication. Yeah, Cartesian table, and we skip the first one because the 0th one, because this is 0, 0. So after this operation, we will have like how many? 9 lists of 2 items: 0, 0, 0, 1, 0. -1, then 1, 0, 1, 1, 1, -1, and the same for the third one. But we don't want 0, 0, so we skip this. Then state variable. So yeah, state variable. So we want to keep this state, but we don't need it outside of the loop. Right? It's used here and there. So next and last. So basically, these 2 lines save us from going outside. Right, so if this one plus something is below the again unless, so yeah, you have to read it and negate it. So yeah, basically, yeah, if you are outside the matrix after this, if the neighbor is outside the matrix, right, the first and the tail is basically so here the $_, the topic variable, will be a list of 2 elements, basically the coordinates of the neighbor, the relative coordinates. So you have to add them to the current position, basically to x and y. You add that, and instead of using the 0 and 1 index, you can just use first and tail. Basically, you take the first and last elements. So yeah, there are only 2, so yeah, the first and last are the only options. Right, so yeah, that's interesting. So you skip if it's outside of the matrix, but if it is inside, then you do this. Neighbors is true if the basically the element at the position of the neighbor is x. Why is it x again? And if last take, so yeah, if, so yeah, after last, when do you call this block? When this block is activated, right after this for, right? So you take the x and y if there was no neighbors. Okay, so this neighbors actually means that there is neighbor in x. Yeah, so you set it to true. Yeah, and actually after you set it immediately, you can immediately stop this internal loop, right? Because yeah, if you found one neighbor, you don't have to scan the rest. But nevertheless, so I take in the pair. So you see, look at the syntax. You just take a pair, x and y, if there are no neighbors. Right. So let's run this Raku JSON. Raku 2. So there are two matrices, 1 and 2. These are the numbers. Okay. So yeah, yeah. We although we have those coordinates, maybe we don't actually print them. So we have the information, but we hide it. Right, so let's maybe before going there, we can say coordinates, and let's run this Raku test. Right, you see, so 0, this is number of row, the 2 is the number of column, and index of column, and here are the two elements in the second example. Right, so this works, and it's a really interesting solution with really interesting elements. Right, Jan Krnavik, no solution here for this task. Mark Anderson, and here we have the right, so the two basically tests immediately, and again notice the syntax. So this is how you can create a small array just by quoting single words in it, and those words are basically one character strings. Then this is the function that does the job. It takes the matrix again, so yeah, you can just pass the two-dimensional array to a function in Raku. Result, okay, results, we're gathering something and we take something. So what we do here, we scan the matrix row column, and right, so this is basically from 0 to the number of rows, and this is from 0 to the number of columns in the first line, but actually yeah, all the lines are equally long. If matrix at the current position gives us x, then so yeah, we skip immediately if like we are like RC point to like this, for example, element of that element. We don't want to. This is not a lonely x by definition. This is not x, right? So you take the coordinates unless any of these again yeah, nice, but it's it's a similar idea with different elements. So the idea is again to use this any junction, and if any of these equals x, you take it. Well, actually, do you take it if it's not x, right? Yeah, probably I would say like if all equals 0, so like negate everything. But well, for me it's easily it will be easier to read if it's like direct if, and this is all, and this is, yeah, in this case it's if all of these equals 0, right? So yeah, even this one is kind of positive. This is all, this is if, yeah, okay, but this is also good. And what we have to notice, okay, first of all, there's like two pair of square brackets to subscript the index in the second dimension, and this is to prevent going outside, right? So if you hit the the out space, you assume that there's like an empty element. So there is an element, but this is an empty element, right? So just to not get a mistake. Right, so if you print 0, yeah, if the number of elements is 0, otherwise you just print the coordinates, right? So this is, and here you print the result. See, so in double quotes you can just use those curly braces just to have some piece of code, of Raku code, directly in the string. Right, so let's run this code. Raku Mark Anderson Raku 2. Right, 1 and 2 and row 1 and column 3. You see, so there's +1 just to make it human coordinates instead of computer indexes. And here is the second answer. Right, okay, so good. Markus Holzer, I hope something interesting is there, right? Well, the only thing probably I don't like immediately is that the style that the closing bracket brace is at the end of the line, like here, here, and here. No, there's no line here. Where is it? That's why I don't like. I cannot find it. Right, this one probably. Yeah. Okay. Good. So there's the input file. Probably we have to look at the list of files. Raku Twitter. Yeah. So here also likes the solution. It's kind of golfish solution which should fit the Twitter, the tweet. Right, but it's more difficult to read because the variable names are just one characters. So this is I was looking for, right? So this is the input, so we have no spaces there, and this is the second example. Okay, let's go back to the solution. So we have this file path. We take this file, we create the IO path object, we read the lines, we map all those lines, and we apply basically the comb function to the lines. So we split this into letters, and we've got this two-dimensional matrix already here, right? That's amazing how you can just read with one line, actually quite clear line. All the elements are transparent, and you've got the job with no loops. Well, there are loops, but yeah, you don't see these loops in the code at least. Right, then you print DD is the recruiter specific, which probably we have to introduce back into Raku because yeah, it's really useful. Yeah, well, if we will ever have any other compiler, I hope we will. Right, so this one is really interesting. So yeah, although this is just the thing for print the matrix, and it's not that important for the task, but this is the important thing that I wanted to point out, because like in the previous example, did you remember that the first thing was just the matrix, the range based on the length of the matrix and of the first dimension of that matrix, and the second thing was just like input square bracket 0 dot elements, right, or without elements. But this is also a smart trick. I like it even more than just going to subscript the matrix. Just take the head element, actually is the zeros element, right? In other in both cases, what you've got here, you've got all the coordinates. So those x and y, they just basically will scan you. This construction will scan the whole matrix. Okay, so but we're going to grab something. I don't quite understand. So actually, so this is. I said it's not important for the program, but this actually this is important, and this is the heart of the start of the program. But DD just probably just prints the result of it, right? So yeah, a bit confusing was for me, as I expected. Like this is kind of a debugging output or just some output, but actually the main job starts here. So we scan the matrix, and inside, then we just grab the thing, basically. It goes over indices, so we grab the coordinates, right? The pair of coordinates, and we take this pair of coordinates into a pointy block. So pointy block is basically an enormous function with this with this signature xy, and we can use those parameters inside this function. And this function is from this opening. The function body is basically, this is what I selected. Right. So input equals input at this position. So basically the current element equals x, and input stands alone at these coordinates. Right, so if we know, so you see, so this AND boolean thing, it should be a short circuit, right? So if this one is true, we're going to evaluate this one. If this is false, we even don't bother about evaluating the second thing, because the whole thing is already false, and we will not filter it. Actually, we will filter it out. Right, so so this function, right? See, so that's the trick. What's called method op, right? So actually, this is a function, but we are calling it as a method. And wow, that's tricky. So this is a function, right? If you call it a function, you have to pass three parameters: matrix, x, and y. By the way, see, matrix is a scalar variable, but it's not a monad. But if you want to call it as a method, the method assumes that you pass the reference to the object in the first argument. So basically, this matrix is kind of the self variable, and it will refer to this object, so as a whole. So this matrix, although it's a scalar, it refers to the matrix, two-dimensional, right? So basically you call this as a so this one is called method operator. You call a function as if it would be a method. Right, so xy and just pass as regular function parameters or arguments when you pass it. So state, maybe neighbors, so potential neighbors, these are the coordinates of potential neighbors. Yeah, just list directly. Yeah, why not? Why bother computing those things? Right, there's the sub and sub is sub. Yeah, if you only need it here, it can be defined there. Okay, so maybe neighbors, grep is neighbors. So you see, so this function with this ampersand is referred to basically to a separate function, and we're grepping these, and what are we returning? Basically, we're returning the result of this grep, right, by this function, and it will be here. And actually, it's not like, so this circuit will evaluate this, and after that, evaluate that, and if it's true, I believe this second result will be returned. It's not like only true and false, because we are going to print this, right? Let's see. Right, so, and finally the function is neighbor. C is the coordinate. You see, so there's no parameters passed here, but basically these are the coordinates, and these coordinates basically are these pair of elements, yeah? So this, yeah, so you take the coordinate of the neighbor, and add it to the current position you're scanning where you're scanning the matrix at the moment. All those are only 1, -1, or 0, right? And the second coordinate again, so you see, so here's the semicolon instead of a pair of brackets. Right, and then this is a really smart thing of using and then here in this position. So you just test if this one is defined, and then if it is defined, you do some other check. So you check if it's x. If it's not, you just don't do this check, which is really like a good example of using this and then thing. Right, so and after that, so basically this is true and false, which is involved here. And if it's false, why not using false? Probably just because of trying to save some characters, or yeah, but nevertheless, let's run this, and we need the function. So I forgot the name. It was Chi2 input and input 2. So Raku, Markus, Raku, Chi2 Raku, and the same thing with input. So right, so you see, so yeah, this is, yeah, well, maybe the output is a bit like computerized, less human than it could be, but nevertheless, so you see there's the sequence, and actually, yeah, it's just confirms that this scene is, and the whole construction does not give you just true or false, but just gives this evaluated result. And let's maybe this second thing. So for the second matrix, we found 2 lonely axes. Right, so it works. And again, I'm completely, personally, I'm completely fine if it doesn't solve the task as it was defined. So the task says that you have to print the number, but actually the solution is really interesting. So this is what is most important thing. Right, P6 Steve. Again, a name which was not there for a few weeks, I believe. Right, so there are... what is this? This is a window, and there are 2 matrices. And you see, so yeah, this is kind of sigilless stuff. But actually it's just a raw thing of X and Y and O characters, right? So all those things. I would say for me it's a bit like Y. Just use a pair of angle brackets, less and more, and you will save, well, these two lines, and also you don't need these commas, right? But this is also a possible solution, why not? But nevertheless, so let's see. So there are two matrices. These are the examples we are going to work with, but there's also window, and I believe what we're going to do is that. And you see the window is the central, we have the 3x3 matrix with the X at the central position. So basically, this is the pattern that you have to find if you think that this X is a lonely thing, right? So you can apply it here, and if you match at least where those two matrices cross, if all those zeros and X's match, then this is the lonely thing. Okay, X walk. You pass the matrix. Again, you pass a two-dimensional matrix in a single go as a single variable, and you can have more arguments, more parameters after this in the function. So you scan the columns and the rows with just straightforward loops, C-style loops. You skip the loop if the element of the current position isn't X. We're not interested in zeros. Then you take this window and you scan the window, right? Columns and rows in the window. You skip if, I believe this is some kind of checks if we have an intersection of those matrix and the window placed at that position, right? So we're trying to place the window at the position, right? Because we are appending the coordinate of inside the window to the coordinate inside this M, the matrix, right? So this scene is actually the coordinate matrix versus window, right? A window applied to this matrix. Then this is the same coordinate, the second coordinate, and again, if it's outside, we do not do any computations. Right, then actually, if this is I don't quite understand. So here you take this, you copy the matrix, the window matrix, and here you modify that. So basically, you take the thing and you save it in the matrix, and then so this matrix, so you kind of create a, I don't quite understand what, I kind of have an idea, maybe it's some optimization, but I'm not sure, because this matrix, I believe, is assumed to be like the new one, right, every time for each cell in the original data. Right, nevertheless, so we copy the element to the window, and if this element in the window which we just copied, I mean, why we need to copy that? Because we can immediately check it here, right? So we increment the counter, the horizontal counter, right? The X hits. If this element is X, basically, if this is not, so all this is executed only for those elements in the original data which are X's, and this one basically counts the number of X neighbors, right? And if this X neighbors is less than 1, basically 0 here, then we can increment the counter for the answer. Right, okay, the only thing I don't understand why we need this copying, because, okay, nevertheless, wait, this is X, right? So basically this is this X, right, the pattern. But we already broke the the window here, right? Okay, just run. I will just run big Raku P6 Steve Raku Ch2. The matrix is built in, and the answers are 1 and 2. These are the original data from the input. So 1 is here and 2 is here. Good. Okay. Alright, so yeah, and the solution is just straightforward, scan everything and find the answer. Okay, Shahed Nooshmand, wow. So there's the matrix, the input matrix. The answer should be 2 and, right, say 4. So we're saying something 4. We scan the matrix, we saw this pattern earlier, we grab it, and in the grab we have this pointy block which ends here, I believe, right? This is for... actually not here, right? There's another grab here. So we scan this. Then, if the current element is X, the one that we want, and not all this, what is not? So we scan the neighbors again. We saw this pattern. Grab coordinates, basically the things that we have to add to the original coordinates of the current cell. X or Y, the junction. So, yeah, okay, so Y, right, so basically you can add plus here, right? No, you cannot. So if both of them are true, basically are not false, right? Not like they're true, but they're not false. So basically, I believe this is to skip the pair of 0, 0. We saw in one of the previous solutions, these were sorted differently, zeros in the first position, and we just take the slice starting from the first element to the end of this list, of this array, of this list. And so if this is not the central position, basically you can also like check if this is not 0, right? Or if this one does not equal these original coordinates. Nevertheless, then we do, if you do, then you basically will return it in the end. This one is X with the so with this, good. So we immediately test if this element is defined. So if we are within the borders of the matrix, and then we check if this is X, right? And after that, we negate that. So we want all the existing elements, which are the neighbors of the current element and are not the current element. They're all not 0. Right. After that, we can just print that. And I believe we will print what we will print. We will print something from here, which are the coordinates. Well, I think it's Raku, Shahed. So we don't have the number of the elements, but I have the coordinates, which is also really good. 0, 2, 2, 3, 0 is the row, 2 is the position, and 2, 3, yeah, these two elements are found. Right, good, really, really good. Okay, Simon Proctor, Raku solution number 2. Here it is. So, right, what are we going to do? We are going to take the widths from the command line. Then we are going to read the cells as a single line, right? But this single line we are going then to split by using rotor and the widths as the widths parameter into the grid. And those cells can be either O or X, and I have to all be one of those. Again, another junction example. There should be at least one element, right? Those elements should be non-zero or true. There's no, sorry. If the number of elements is, yeah, so I thought these are ampersands. Maybe yeah, too many double characters. I mean, the designer of Raku didn't think about that, right? So that I can assume that if these are ampersands, that these are also ampersand because these are here, but these are actually not ampersand. So the whole condition is this one. So if the number of elements is divisible by widths, so if we have enough elements for filling all the rows, and if the number of elements is bigger than the width, so we filled at least the first row, right? Okay, so we've got this matrix, and we print it if we want to have some debug information. Then the count is the answer, which I'm going to print. And again, so you scan this. That's another pattern. I don't know why we need this 0 and ... Probably it's completely redundant, but it makes the program completely clear. We're going from 0 up to, but not including widths, and here up to, but not including the number of elements in the grid, right? So this is the X coordinate, this is the Y coordinate. We multiply that. Oops. we do not multiply that, but we create a list. Yeah, so we multiply and cross multiply and append and apply the comma operator, so it will be like 0, 0, 0, 1, and so on. So this vector is the vector, and each element of that is the coordinate, right? So there should be 2 elements in this. So basically, the first and the second coordinate. Yeah, again, so because we scanned it in this direction, so the first coordinates is the second coordinate, and vice versa. Okay, so we increment the counter if this element is wow. Wow. That's cool, but I don't understand that. So if this element is x, right? Okay. But this one and none of the surrounding. Really? Wow. That's cool. That's cool. So basically you have to I have to play with this separately, but I like this. Okay, so if none of, again, the non-junction, I believe, none of the surrounding cells which surround the grid at the current position, right? Okay, so this is what we have. Again, the same construction with x comma. So we create like pair. Well, it's not pair, it's a list of 2 elements. -1, -1, -1, 0, -1, 1, and so on. We skip, so we grab everything which is not 0, 0. Maybe this one. So yeah, the thing is that this is a perfectly compact thing, but this is not. Probably, yeah, we have to make it somehow differently. Like that all, right? That all is not 0, probably. Then you map, so you compute the coordinate of the cell that I want to test, well, those neighbors, right? And you grab only those where we have something, right? And none of surrounding elements. So basically, this thing will return you the coordinates of the elements, if I'm correct, and none of them should be x. That's vec. Where is vec? And where's the grid? Do you see the grid here? Oh my god. I was telling you an insane thing, right? So this is the function which is called here, right? Surrounding cells. Right, so, but then you call this function surrounds. Yeah, we know how this works. So it returns you the coordinates, and then you map those coordinates, and those coordinates, basically the coordinates of the existing neighbors, we have them here in xy of the this pointy block, and then basically you get, so you map those coordinates, you map that vector to basically the element, and you grab only those which are defined, right? And after that you match that with x. Wow, yeah, a bit maybe difficult, but I believe it perfectly works. Raku, Simon Proctor, Raku Chat 2. What do we need there? So, so widths, okay, 3, then 0, 0, okay, 0, 0, x, 0, 0, 0, x, 0, 0. So I made a matrix of like 3 by 3, 3 elements, 3 elements, 3 elements, and the answer should be 2, because these 2 x's are lonely. The answer is 2. If I will do it like this, the answer should be 1, right? Because these 2 are not lonely. Yoo-hoo, right. Really good. Okay, it was Simon Proctor. Right, the next solution is mine solution. Let me show mine solution in the Raku programming language. Yeah, basically you saw all the elements of already, so this is where I define the matrix. Actually, yeah, I made a simplification. I assume that the matrix is a square thing. Yeah, actually the examples are square. So yeah, it will not work for like 3 by 4 matrix, but nevertheless, so again, so these are the coordinates of the neighbors. So this is what I do. Yeah, so probably, actually maybe I gained some characters. So instead of just having this -1, 0, 1, x, capital X, -1, 0, 1, I just use this. So I duplicate this thing, and I just then apply the cross thing. Probably I gain a few characters, yeah, but that's probably not it made it less readable. And then I grab all the things which are not, so this is, see, so I just mentioned the previous solution that probably can use .all. All the elements of these pairs, let's call them pairs, which are not pairs officially, but the pairs like pair in sense of pair of coordinates, they are all non-zero, right? So they have to be at least, wait, all non-zero, but one of them can be zero, right? Any of them is, no, all should be not, yeah. Okay, nevertheless, I believe we can just prove this by Raku, by running it from the command line, right? So let's see. So yeah, see, so there are 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 pairs of coordinates, right? Okay, and after that you scan the matrix. It's a square matrix, so yeah, I don't have to basically, to make the solution suitable for non-square matrix, I have to put the square brackets 0, for example, or dot head, which I also like, or dot tail actually. Then this is a coordinate x and y together, and this is, I don't like this part. Well, probably I can make it a bit cleaner by removing this one and replacing it with a single semicolon. But I want a better way because I have 2 coordinates here, and I want to subscript the 2-dimensional matrix with this item. I don't know how to do that. Probably there's some interesting trick. If you know, let me know. Right, so I skip if this current element is O, right? And after that, I print the coordinate, right? I print it like this without parentheses, not say but put. If all, again the junction, if all things basically are true, right? So, and what I'm testing if the matrix at the given thing will return to the given coordinate are zeros, right? So if all the neighbors are 0. And how do I do that? So first I apply, so I call the map method on the neighbors. So for all the neighbors from here, we just saw these are the coordinates of neighbors relative to the current position. I use this thing. So I basically, like in a single go, I increment both x and y coordinates because I have 2 coordinates here and I have 2 coordinates there in the neighbor, and that's it. So yeah, not like $_0 plus chords bracket 0, but like with this, I think this is fine and cute. After that, I grab if this is within the borders of the matrix, and then I map this, and yeah, after that I want to make sure that all of them are true, and then I print, and here is the output. So let's run my solution. Raku ash Raku ch 2. It prints 0, 2 as the coordinates of this lonely x. Yeah, again, I don't print the number of them. Right, okay, so Athanasius, Raku number 2. Here's the solution. So here's the solution. The main function starts here. So what I want rows where the number of elements in the rows are positive, and the number of characters in each row is, so basically what I'm reading, is there an example of the input? No, I don't think so, but we will, yeah, guess it. Right, so the array of strings with rows, matrix, get matrix, and this is how we deal with the input. So we compute the widths, we, what is it? It's, wait, what that means? My array of strings, matrix. So this is where I define the size, right, of the add matrix variable, if I'm correct. It looks like, okay, I mean, it doesn't look like Raku, it's, if I understand this line correctly. Then you scan these rows, you take the current row. Good. So if invalid character, so we check if the row only, so yeah, this is, you see, so the minus means negation, and this construction means the character class of regular expressions, right, within the regular expressions. So if we have anything outside of these characters within the class, then we raise an error, and the same we check if all the numbers, all the widths of all the rows are the same, right? So they're equals to the first row, and we return the matrix. Right, so this is where we were get matrix here. Then we print the matrix. Let's see how we print that. Oh, that's yeah. So we just prepare some strings using printf. We print them for all those matrices, for all those indices in the matrix. Basically, we scan the rows, right? I'm a bit like, why is this starting from 1, not from 0? But let's see. Okay, then so get where was I? Get print find lonely x, and the count is number of elements in those lonely x. The output, we print the counter, and for all those we increment the counter and take the key and value, which we are going to use, I believe, here and there. We print them together with those coordinates, and we just have like the first is this, second is that, and so on. Okay, so find lonely x, the main subroutine here. So it takes the defined array of defined strings matrix and returns the defined array of defined pairs. So here the real pair goes, the real type pair, lonely x. Right, so matrix, so these are the dimensions. We scan everything, the label. We are going to like next column, right? Because if you have next here, you will start the next iteration for this loop, but we want for the, actually there's not loop, and we want outside of that, right? To go outside of that. So 1, 2, 3, 4 in nested loops. So we scan these rows, we scan those columns, that's fine. If this, right, so yeah, instead of just, I believe like syntax with next is cleaner because you don't have an additional like indentation level, right? So if this is x, you do this, and what you do if you found this, so yeah, so if row delta, okay, so yeah, we scan the neighbors just in 2 separate loops, and we list the coordinates of the neighbors just in separate lines. And here we compute the absolute coordinate of the cell here and here. No, here and here. And if it's outside, other outside and left side, right side, here, here, or like below or above the matrix. We do not want to do anything, and here we have next. Oh yeah, actually we can have if here, and do the same trick as we did here. But yeah, and here we skip the basically current. So if we do not move, we don't want to test the same element with itself. It will always give us the false result because we don't want x at that position, and the current element is always the x right here. Right, and finally, so yeah, next, this x is not lonely. If we see that the element at that position that we just computed here and here is not x, then yeah, this is, we can continue. If it is an x, we can break immediately, and right. And finally, so next column, so if we break here, we will not reach this line, but if we do not break here, we basically reach this line, and we collect the pair that contains the pair of coordinates. Right, okay, so what we need in the input, same, so yeah, I believe we need like strings. How do we read them? Characters, right? So yeah, do we have any right, so this is, I didn't see it. So yeah, basically this is the equivalent of the comb method. We split the strings into characters, and we assign this to this matrix row, right? So what we need Raku, Athanasius, Raku 2. So like this. So the answer should be 2, and the answer is 2, 1, 2, and the output. So this is the matrix. So see, yeah, I like the the enterprise style of these solutions by Athanasius, and I really like the everything is really like step by step. Everything is clear, perfectly, like no steps right or left. Everything works. Although the solution is quite long. Okay, good. Going next, Colin Crain, Raku 2. Here is the solution. Aha, nice. I like this. So we just saw, and we immediately understand what this means, right? So this, I even don't have to explain. I just have it here. Right. So if input is empty, we make this input the default. So we give it some default values. The matrix, we map those, and we comb these things. So basically here we have two-dimensional matrix again. So we see how easy it is to do in Raku. Then work starts. The number of elements. Yeah, so that's probably one of the first times when we really scan the x, y in the correct order. Well, yeah, of course there were earlier solutions, but I believe in all the other things we scanned rows first and columns second. But here is just x and y in the alphabetical order. Right, so these are the coordinates. Again, the pointer block with the signature. If this matrix element is x and it is lonely, we just collect the coordinates. And how do we determine if this is a lonely thing? Here we determine it. Oops. Why is it? It's a Raku solution, right? I wonder why you do need these constructions. So it's a signature. So just put this xy here. It's not Perl. Right, but I kind of reckon that this is right. So this is exactly here. Copy-paste solution from Perl. Copy-paste transformation. Right. Okay. So nevertheless, so we've got these coordinates. We cross multiply. How do we do that in Perl, by the way? I believe there should be. Right. So here we just list, and here we can just explain how we get that list, right? We cross these positions. We grab if it's not equivalent to 0, 0. That's a nice thing. All right. There's the offset, which is relative to the current position. We skip if it's outside the matrix, and we return 0 if the element of that position is x. Right. So we see that this is not a lonely thing. Right, and then where will we? Right, we push this, so we have this lonely array with the coordinates of lonely elements, and then we just print it with nice arrows. Wow. Okay, I want to run this, and I don't need to enter anything, at least for the first run. Right, the x at column 3 rows down 1 is lonely. This one. Yeah, and maybe now I want to, because I already have this. Yeah, 2 elements are found. Good. Going next, Laurent Rosenfeld, Raku solution. There's the matrix. I don't understand why we need these square brackets. There's another test, right? Okay, then what do we have here? Here, we start here, so we scan the matrix. Again, x and y in correct position, but I and j in opposite. We skip if it's not x. We push the result if the check. So the kind of skeleton of the program resembles the previous program. But the check function, it's here, so it takes 2 integers. Type restricted variables. So we scan the neighbors, and if we skip if it is the current element, if we are not going to visit the neighbor, if we are on quarantine, and then if it's outside of the matrix, or yeah, actually, so if it's kind of out of the matrix but in like on the left or above the matrix, right? If the index is negative, but if it's positive, we do not check how positive it is, how big it is, but just check if the element exists. But I believe we can just skip this one, because in Raku you cannot use a negative index, right? Okay, so yeah, it will. I believe we don't need it in Perl. Okay, so too many pills here for the Raku review. Okay, so no, actually exactly the same. Right. Because we saw in some previous solutions that we just check if the element exists, and we don't care about the element, about the index, right? Right. Return false if this is an X. Right. Okay. Let's run this. Yeah. So and then we just push result if check gives us true. So this result. Actually no. Yeah. If the result has some elements, we print the result, not the number of elements. Yeah, which is what I wanted to see. Laurent Rosenfeld Raku Shitov is default built-in thing. So these are the coordinates of the lonely axis. This one and this one. Okay, going next. 1, 2, 3 solutions left. Mohammad Anwar, Raku number 2. So we read rows, number of rows, number of columns from the command line. Default are 3 for both of them. Find lonely x. Is copy. So yeah, this is human, this is computer indices. Right, find lonely x. We pass the matrix. Where do we take the matrix? We get matrix here, and we use those things right from the input. We have this array, and then we build a matrix by just filling this. We are picking. So it's not we're just scanning this. We're picking the random thing right out of these. Good. Probably, yeah, I believe we can do something like xy dot pick, right? X comma 0 parentheses dot pick. We can just choose random element out of those two. But nevertheless, right. So display matrix just in a loop with printf. And right, so we've got the matrix here. We pass it here as a scalar. We determine the basically the dimensions. We scan the matrix, and this lonely is empty first, and we are going to return the flattened thing of this Raku Raku array. Right. So how do we do it? We scan the matrix. We have these maximum positions. Next unless this is X, right? We skip that, and if it's neighbors, then we push some things. Then we push some things, and we push basically the. We push the element, right? So we push the element neighbor if we are within the borders, right? And after that, we grab those neighbors. We only contain those X, and we push the coordinates. Unless neighbors, so right, so these neighbors are the X and zeros, right? X and O's, if any, if they are within the borders. So we just list here in these neighbors all the neighbors. We have a list of them here. Right, and then we grab those which are axes, and we push the lonely axis. Really? I don't quite understand that. So we've got the neighbors, so we've got all those things, and they can be both X and Y, right? And these are the elements that surround the current element, the current position row and col, and we push this current position, well, yeah, up to with this one, for all those elements which are axes, right? Okay. Why is it lonely then? I don't understand. And we only scan the matrix, and we for each. So okay, so this is the code which is executed for a single element. We find all the elements around this, and we grab those elements which are around our current X, which are also X's, and we put those coordinates there. Okay, let's run this. I'm curious to see what's there. So I believe we will see Raku the matrix, right? Because otherwise it will be difficult to understand how it works. So this is the matrix. There are nothing. Like all the elements are not lonely. Here we found two lonely elements. This one and that one. Here are the coordinates. This is the correct result. Wow. Next, unless it is, so here the current element is X. Wow. Okay. Maybe can I just see this neighbors array, because I don't understand how it works. So I want to say neighbors. English spelling is hard. All right, so let's go Raku T. Voila. Here we are. So these are the neighbors. So maybe let's find an example where there are some lonely things. Everything is 0. Everything. Okay, so we found here. So 0, 0, 0. These are the three elements around this X, I believe, right? So we scan the matrix, and the first element we found is this one. There are 3 zeros, right? These are the elements around this. So these two, these vertical 3, and these two, right? Yeah, this, that, this. No, this, and these. Then around this element, there are like X. Okay, I don't quite understand how this works, but nevertheless, so yeah, there are like 1, 2, 3, 4 zeros and 1 X around this one. Okay, so we only are interested in things where we have like all the neighbors which are 0, right? So here, unless, this is unless. Okay, now I understand. So yeah. Yeah, well, I really like unless, but like today I already make the second mistake that I just ignore the meaning of unless in my head. Okay, right. So if there are no x's basically around this thing inside these neighbors basically, then we skip this thing. Okay, good. Right. So the next solution. Let me read this. Myoungjin Jeon. Yeah, I have to find the pronunciation. Okay, right, so we have this usage information and the main thing. So this is how you pass these things. So this is what you expect, this program expects, right, in the input. Matrix read lines, split using these things, split rows by a new line or square bracket. Then map, skip empty line, and remove unused characters. Okay. Then the matrix 4. So if there's a matrix, yeah, with this matrix you do. So in the matrix actually is the topicalized thing here, so it's inside $_. For the dimensions of the matrix, if the current element, you see, so this is, that's, by the way, it's really interesting thing, so you can just call the dot on. This is probably where you really want to have a dot. Like if you have $_, you can omit $_ and you can just call this thing. Yeah, now I understand that this dot is useful when you are working with the topic variable. So okay, so if you see the x, you skip. If you don't see x, you skip this loop. If right, so this is where dy dx, mathematical notation, I like it. So if this is 1, so if the result of this is 1, right, because you map this, and so this is the shift, vertical horizontal shifts, and this element exists, that's the so simple check. And if that element exists, and if that element, finally we can check that. Yeah, so if like the row exists, and then if the element exists, and if it's not, so if it exists, you take either the current value of this cell, or you take the O. And again, as in the previous solution, we grab the thing on that. Yeah, see, so yeah, it's nested call with the dot. And right, and finally, if there's only one element, okay, so I believe, right, so we're not, that's also smart. I think we saw this for the first time, so we don't need to skip the current, like when we are visiting the neighbors, here we're just taking all the neighbors, including the current element, and if in the end we see that there's only one x, then this x is a lonely thing. So yeah, we count all the x's in the square 3 by 3 around this current position. We kind of ignore the value of this current position, but we know already that this is x, but we just count all the x's that we can see here in this square, and finally we see that there's only one element in this square, then this is the lonely element. That's smart. I like this step. And probably I need this one. Okay, so definitely I would do it differently, but nevertheless, but I need this one. Jeong, not here. Jeong Raku 2. Right, so this is the matrix. Where's the output? No, this is not a good example. So I mean, this is a good example to have no lonely x there. And right, lonely x at row 1, column 3, and at column 3, column 1. Good. Okay, so yeah, it works. So the thing, the interesting, actually the new thing I believe, right? Probably I didn't see this in the earlier solutions, is that we do not exclude the neighbor, so we treat the current element as the neighbor of itself. Right, okay, Roger Bell West. Actually, it's the last solution because there's no solution here in Raku. Raku, Roger Bell West. Here's the solution. So we have two test cases, right? So example 2 gives us 1 lonely x. Example 2 gives us 2 of them. So we take the array again. You take an array, the whole array is a single thing. Actually, it's a two-dimensional array, the matrix. These are the dimensions. You scan the matrix, you skip. Why so difficult? Like next and less. So you skip the element if it's not x, isolate it, the synonym for lonely. You scan. So we saw this pattern. So two different, two nested loops with all those 3 coordinates. We skip it if it's outside, outside of the number of rows, right? And we should skip it if the current element. Yeah, here we skip the current element. This is where we skip the thing if it's not within the borders of the row. And finally, if we found an isolated thing, actually if we found that the thing is not isolated, we set the flag to 0, to false, and we stop everything. Actually, what do we stop? We stop this one, right? I believe. Right, and finally, if the isolated, we increment the total number of isolated items, and that's it. Okay, so let's run this. It should just print OK1, OK2, Raku, Roger, Bell West, Raku, Ch2. Voila. It works. Okay, so that was the solution. Definitely there are more ways to do that. But nevertheless, I really enjoyed looking at these Raku solutions, and I hope you also enjoyed it. Okay, see you next week with more Raku reviews, I hope. See you.